Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today we have set our hearts to solve an ATP paper. We call it paper 4. And for this purpose, we have selected May June 2024 4-1 paper. So the time allowed for this paper is 1 hour, and the the marks for this paper, they are 40. So let's start today's paper. So on your screen, the May June 2024 4-1 paper is showing up. The time allowed for this paper is 1 hour, and the marks for this paper are 40. So let's start the question number one. A student finds the volume of a small glass ball, marble, which is the made of marble, by two different methods. Method number one, the student places 6 small glass balls by the side of a meter rule as shown in the figure 1.1. Makes sure that there are no gaps between the balls. Take readings on the meter rule of the positions of the point A and B shown in the figure 1.1. Give your readings to the nearest 0.1 centimeter, the position of the point A and the position of the point B. So you can see we have placed 6 marbles by the side of a meter rule. So they are starting from here. This reading is, if you look at it carefully, the reading is how much? 10.2. And this reading is here on this end is 19.7. So we will enter these values. The position A is 10.2 and the position B is 19.7. So if you can look at the mark scheme, our answer is right. Okay, so this was the A part, its first portion. Then he says the length L on the figure 1.1 is the distance between the point A and the B. The average diameter D of the one ball can be found using the equation that L is equals to 6D, because there are 6 balls, so there are 6 diameters in that length. So L is equals to 6D. Use your answer to the A first part to calculate the length L and the diameter D. Give your answer to the nearest 0.1 centimeter. Okay, so the L reading from 19.7, we will subtract from 19.7, we will subtract the 10.2. So the L is basically 9.5 centimeters, because the formula is given in this question that the L is equals to 6D. So the 6D will be equals to 9.5. D will be equals to 9.5 divided by 6. D will be 1.583. When you round it off to two significant figures, it will be 1.6. So enter here that the L value is 9.5 centimeter. I hope you understand this. And the D value is 1.6. Our answers are right. You can look at the marking scheme. This is how this is done. Okay, so we are going to the next part. The average, this is the third part. And he says the average volume V, average volume V of the one glass ball using this method is given by the equation. So 3.14 D cube divided by 6. So calculate the V. So very simple, simply put the value of the D in this formula and you will be able to find out. So V will be equal to 3.14 into 1.6 raised to power 3 divided by 6, and that will be 2.14 centimeter cube. 2.14 centimeter cube is the answer. The answer is right. Okay, so then we have question number 1 is B part. He says, now this is the method number 2. And they found the volume of the one marble glass ball's volume by measuring its diameter. And this is the method number 2, in which the student pours water into a measuring cylinder. The volume of the water in the measuring cylinder V1 is shown in the figure. So we can tell how much is this volume. You can see here the volume is how much. This is 21, 22, 23, 24, 25, 26, 27. So the reading when there is no marble in the measuring cylinder is 27. Let me call it V1. So write down the reading of V1. So the V1 reading will be how much? 27 centimeter cube. The answer is showing up on your screen. Let's check from the marking scheme. Marking scheme also says 27. So this is how you write it. Okay, then they say the 6 glass balls are carefully added to the water in the measuring cylinder. The new reading on the measuring cylinder V2 is shown in the figure 1.3. The volume VT of the 6 balls is given by the volume of the 6 balls, which they are calling is VT, that is V2 minus V1. If you look at here, what is the reading V2? That reading is, I think, 39. So that reading is 39. So from V2, we will subtract the reading V1, that was 27. So the VT, the total volume of the 6 balls will be V2 minus V1. We will just put the value of the V2 and the V1, and then we will be able to find out. Okay, so the reading of the V2 is 39 and V1 is 27. So 39 minus 27, that will be 12. So the volume of the 6 balls is 12. So what will be the volume of the one ball? That is the main question. Okay, so our answer is right. Okay, so let's go to the next part, B, question number 1B. And calculate the average volume of one ball using this method. Give your answer to the nearest zero point 0.1 centimeter cube. I know the volume of the 6 balls. Now I can find the volume of the one ball. The volume of the 6 balls is 12. So I can say the volume of the one ball will be VT divided by 6. That will be 12 divided by 2. 6. And that will give you 2 centimeter cube. So the volume of the one ball is 2 centimeter cube. So this answer is right, sir. Okay, so we are going to the next question. He says, suggest whether the method 1 or the method 2 gives the more accurate value for the volume of the ball. Explain your answer. We think that the method number 1 is more accurate as compared to the method number 2. You see in the method number 2, we are using measuring cylinder, and that measuring cylinder, the least count of that measuring cylinder is 1 centimeter cube. That measuring cylinder cannot calculate any volume which is less than 1 centimeter cube. So this answer is only accurate up to 1 centimeter cube in the method number 2. Whereas in the method number 1, when we measure the diameter, that diameter was measured accurate up to 1 millimeter. So 1 millimeter will become more accurate when you calculate the volume with it. That will be more accurate because you are measuring diameter accurate up to 1 millimeter. So this is what I think. Okay, so let me write that, show you how I wrote that answer. So my answer is the method number 1 is more accurate as compared to the method number 2. And the explanation is in the method number 1, the diameter can be measured accurately up to 1 millimeter. In method number 2, volume can be measured accurately only up to 1 centimeter cube. So when you find the volume on the basis of which is accurate up to 1 millimeter, so that will be more, it will be giving more accurate values as compared to the method number 1. Let's check from the marking scheme as well. In marking scheme says that the method number 1 and more accurate is method number 1, as the measuring cylinder can only measure to the nearest 0.5 centimeter cube, or some people will say 1 centimeter cube. We said it can measure up to 1 centimeter cube. Or measuring the diameter to the nearest millimeter is more accurate. This is what the marking scheme is saying. I hope you will be able to write a better answer, but our answer to our best of the knowledge is this. Okay, so question number one is D part. He says the student now uses the 6 glass balls to find the average mass of one glass ball using a small beaker and a top pan electronic balance. Okay, so describe the method the student uses. So we have a top pan electronic balance, and we want to find out the mass of the one glass ball. So what I will do, I will put the beaker on the electronic balance, and I will tear it. I hope we call it that. And I hope I am pronouncing that word correctly. Tear it. Tare, Tare, tear. So you can tear it. Tear means that when you put something, an empty beaker on it, and obviously the electronic balance will show some reading, and then there is a button on the electronic balance. You press it, and the reading becomes 00. And then whatever the thing you put in that beaker, for example, I put 6 marbles in that beaker, and whatever the reading shows up, that after tear, whatever the reading will be shown, that is directly the mass of those 6 balls. And then you divide that mass with the 6, and you will get the mass of the one ball. The other way of doing this is that don't tear it, just simply take an electronic balance, put a beaker on it, and note down what is the reading. That reading, let me say, is M1. Then put 6 marbles in that beaker, and now note what is the reading on the electronic balance. Let me say that is M2. From M2 is the mass of the beaker plus the 6 marbles. Then from M2 subtract the M1, whatever the difference you get, divide it with the 6. You will get the mass of the one marble. So this, I hope you understand both the methods. And so put empty beaker on the top pan balance and note mass of the empty beaker. Let me call it M1. Put 6 balls in the beaker and note the mass of the 6 balls with the beaker. Let me say M2. Subtract M1 from M2. Divide this difference by 6 to calculate the mass of one ball. I hope you understand. Let me show you the marking scheme as well. So you can see question number 1D part, the marking scheme is showing up on your screen. You can pause the video and you can take your time with this marking scheme. This is my answer. I hope you can write a better answer. This is just an idea how to write this. Question number 2, a student investigates how the temperature of the surrounding affects the rate of the cooling of the water. Question number 2A, first part. The student pours 100 centimeter cube of the hot water into a 250 centimeter cube beaker. So he has a beaker, a little bigger beaker, which is of 2 centimeter cube. And he pours 100 centimeter cube of hot water in it. Using a thermometer to take the temperature of the water at the time t equals to 0. The thermometer reading at the t equals to 0 is shown in the figure 2.1. So this is the diagram or the figure of thermometer. So let me show you. I have made it larger so you can understand how we have taken the reading. This reading is, I'm going to take the lower meniscus. This reading is 72 degree centigrade. So the reading is 72 degree centigrade. Record the temperature of the water at t equals 0 in the table 2.1. So in this table, we are going to record this reading. That reading is 72 degree centigrade. So let me show you. I have done this on this paper. So the reading will be 72 degree centigrade. Okay. So let me check from the marking scheme, question number 2. So 72 degree is the right answer. Okay. So, okay. So we have done with this. Okay. Then he says the student then records the temperature theta of the water every 30 seconds. So he poured the hot water, its temperature is 72 degrees centigrade, and the time is 0. He started the stopwatch, and after every 30 seconds, he is noting down what is the temperature from the thermometer of that water. So he's using a stopwatch. Okay, the results are recorded in the table 2.1. By taking each temperature reading, the student carefully stirs the water. Before taking each temperature reading, the student carefully stirs the water in the beaker. Explain why. Okay, so you see, whenever this is that after every 30 seconds, they have noted down the temperature. The water is cooling down. Its initial temperature was 72. So why we stir before taking reading? So you see, we always stir the water before taking the temperature of the water. We want to make sure that the temperature is uniform throughout the body of the water. Student stirs water to make sure that the temperature is uniform throughout the body of the water or throughout the body of the liquid. The marking scheme is showing up on your screen. Question number 2A, second part, and you can check this also. You can pause the video if you want more time with it. Okay, then their question is, this is the third part. Calculate the average cooling rate, C1 of the water for the first 90 seconds of the experiment. Use the reading in this table 2.1 and the equation. The equation is the temperature at the 0 degree centigrade minus the temperature at the 90 degree centigrade and divided by the total time. The total time is 90 seconds because they are talking about the first 90 seconds. Okay, so then I will get the rate of the cooling and I'm calling it C1. You see, if you look at this table, when the time is 0, the temperature is 72. And when the time is 90, the temperature is 66. So we will put the values in this, and the time for this change is 90 seconds. So 72 minus 66, and that will be 6 seconds, sorry, 6 degrees centigrade. And when you divide it with the 90, you get 0.067. So the rate of the cooling is 0.067, and the unit will be degree centigrade per second. This is the rate of change of temperature. Okay, rate of change of the temperature or the rate of the drop of the temperature drop, you can say. Okay, the fourth part, he says calculate the average cooling rate C2 of the water for the final 90 seconds of the experiment. Use the equation temperature at the 150 minus temperature at 240 seconds and divided by the time taken. From 150 to 240, the time taken will be 90 seconds, where theta 150 is the temperature of the water at the 150 seconds and theta 240 is the temperature of the water at 240 seconds and t is the time of 90 seconds. So this time the cooling rate will be called C2. So at 150, the temperature is 64. At 240, the temperature is 61. And the time difference is 90 seconds. So we will put these values there. And here we have C2. So the C2 will be equals to 64 minus 61. 64 is the temperature when the time is 150. 61 is the temperature when the time is 240. And 64 minus 61 is 3. 3 divided by 90 is 0.033. And so the cooling rate, or you can say the rate of change of temperature, and that is 0.033, and the unit will be degrees centigrade per second. Okay, hopefully you understand these things. Okay, so we are going. Okay, so the marking scheme is showing up on your screen. And 64 minus 62. Okay, and then we have the next part. He says compare your values of C1 and C2, explain any difference in these values. The C1 value, the C1 value is 0.067 and degree centigrade, and the C2 value is 0.033 degree centigrade per second. C1 is higher than the C2 at higher temperature. Why this is the reason? You know, the the rate of the temperature drop depends upon the temperature difference between the hot water and the surrounding. So when the water was at 72 degrees centigrade, and the temperature difference between the surrounding and that hot water, the temperature difference between the hot water and the surrounding is larger. So the rate of the cooling is also faster. But when the 150 seconds have passed, the temperature of the hot water has become 62. And you know, I hope 62, I just said 62. I hope it's 62 or 664. 64, yeah. So the temperature difference between when the time is 150 second, the temperature difference between the hot water and the surrounding has become less. That's why the rate of cooling is also, or the rate of the temperature drop has also dropped. So I hope do you understand this idea. Look at the marking scheme. He says C1 is greater than C2 because less drop in the temperature as the temperature approaches room temperature. Okay, so let's go to the next part. Okay, this is question number 2. It's B part. He says the student repeats the procedure described in the A first part, but this time he places a 250 centimeter cube beaker inside a larger beaker containing iced water. You see, first they have done in the experiment number 1, what they did, they took 250 centimeter cube water and beaker, sorry, and they put hot water in it and put it on the table. So it's in contact with the surrounding. So, but now in this B part, what they're saying that we will take a 250 centimeter cube beaker and we will place it in a larger beaker. And in that larger beaker, they are going to put iced water. Now, the temperature of the ice water is less than the temperature of the surrounding. So now when you will put hot water in the 250 centimeter cube, uh, hot water in the that smaller beaker, 250 centimeter cube beaker, it will be surrounded by the iced water. Now, this time, the temperature difference between that hot water and the ice water obviously will be larger than the temperature difference between the hot water and the surrounding air. Okay, so the arrangement is shown in the figure 2.2. So here we have a larger beaker. In that larger beaker, we have iced water, and then we have this smaller beaker. In this, we have poured hot water, and we put a big thermometer in that hot water. The student reads the temperature theta of the hot water, records the reading, and immediately starts the stopwatch. The table 2.2 shows the temperature theta at the time t equals to 0 second, at 30 seconds, 60 seconds, and 90 seconds. So this time the initial temperature when the time is 0 is 75, and after 30 seconds 68, after 60 seconds 62, at 90 seconds it is 57. Calculate the average cooling rate of the hot water for the 90 seconds. Use the readings in the table 2.2. Okay. So when the time is 0, the temperature is 75. When the time is 90, the temperature is 57. And the time taken for this change is 90 seconds. So you see, C3 will be equal to 75 minus 57, whole thing divided by 90, 18 divided by 90, that is 0.2. And the unit is degrees centigrade per second. You can see our answer is right, 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 right. Hopefully you understand. This time the cooling rate is called C3. Describe how the C3 differs from the C1. The C1 was, we know the reading of the C1 was 0. C3 is 0.2 degree centigrade per second, and the C1 was 0.067 centigrade per second. The rate of the temperature drop in the C3 is higher than the C1 because of the larger temperature difference between the hot water and the surrounding. In this case, the surrounding was the iced water. You can write here iced water. Also, the question was describe how the C3 differs from the C1. Okay, so this is hopefully you understand. This is the answer. You can read it also from here. You can also read my answer. I hope. The recorded readings show that this experiment is not a valid comparison of the C1 and the C3. By by referring to the results recorded in the table 2.1 and table 2.2, explain why this is not a valid comparison. You see, in both the experiments, the starting temperature, the initial temperature of the water is not same. For a valid and fair comparison, the initial temperature of the hot water should be kept same. This is my idea. Initial temperature are different. Initial temperature for C1 is 72 degrees centigrade, while initial temperature for C3 is 75 degree centigrade. So different initial temperatures. So this is our answer. Okay. Then we have the fourth part. He says state one other variable that should be kept constant to make a valid comparison. You see, to make a valid comparison, one thing they should keep same is the volume of the hot water. The volume of the hot water should be same. Okay. Volume of the hot water in both experiments should be same. He says volume of the hot water, position of the thermometer in the water, and room temperatures. Hopefully you understand. So here we have question number 3. He says a student measures the focal length of a lens. Figure 3.1 shows the apparatus she uses and the position of the lens when a clearly focused image is formed on the screen. So here you have a lamp. So here you have a it's a card kind of thing. It has a hole in it. So this will act like an object. Here you have a convex lens in a holder. So this convex lens will make a real image of this illuminated object, a hole, on the screen. Okay. This image will be real, it will be inverted, maybe magnified, maybe not magnified, we don't know. Okay. So the distance between the object and the lens is called x. The distance between the screen and the lens is y. The total distance between the object and the screen is d. The student placed the screen at a distance d equals to 60 centimeter from the illuminated object. So the distance between the object and the screen is 60 centimeter. Places the lens between the object and the screen so that the lens is very close to the illuminated object. Moves the lens slowly away from the illuminated object until a clearly focused image is formed on the screen. He says, measure, underline this word, measure. Measure means you have to measure actually. You have to, with the help of the scale, you have to measure and record the distance x on the figure 3 point. So with the help of the scale, measure how much is this length x. And let me show you. I measured it with the help of my scale, and this length was 4.8 centimeter. 4.8 centimeter. Okay, then they say the scale is 1/5 full size. So that means if on the map something is 1 centimeter, in actual it is 5 centimeter. This is the meaning of this scale. For example, here I said the distance x is 4.8 centimeter. So in actual, it will be 5 times more. So figure 3.1 is drawn to a full scale of 1/5 full size. Figure 3.1 is shown drawn to a scale of 1/5 full size. Use your answer in the first part to calculate the actual object distance u from the lens. U is the distance between the object and the lens, that we represented with the x here. So 4.8 will be multiplied with the 5 because the scale is 1/5. So it will be 24 centimeters. So the actual distance between the object and the lens is 24 centimeters. That is u. That answer is right. Then the third part is deduce the image distance v, the distance from the lens to the screen when a clear image is seen. You see, the distance between the object and the screen was 60 centimeter. and this x is 24 centimeter. So this y will be d minus x. Y will be d minus x, and so I can calculate it easily. So here v is equals to d minus u, that is 60 minus 24, and that is 36 centimeter. V, which means the distance between the lens and the image, the lens and the screen, that is 36 centimeter. Answer is right. Okay, so then we have, this is the B part. Is a figure 3.2 shows the shape of illuminated object, and the figure 3.3 shows the image seen on the screen. Describe two differences between the illuminated object and its image on the screen. So here is that object, this is its image. You can see the image is small, the object is smaller, the image is larger, so the image is magnified. Another thing, very clearly you can see this is inverted, upside down. Another thing which happens here is the image, inverted image as compared to the object, image is magnified. They say this is upside down, inverted, laterally inverted, bigger than the illuminated object, or you can say magnified. The student moves the screen away from the illuminated object and repeats the procedure for the values d equals to 70 centimeter, 80 centimeter, 90 centimeter, and 100 centimeter. The table 3.1 shows the values recorded. Add your values for the u and the v for the a second part and a third part to the table 3.1 on the page number 12. Complete the table 3.1 by calculating the value of the u multiply v for each value of the d. Give your answer to three significant figures. Okay, here we go. So here we have this table. The u is 24, the v is 36. Then we will multiply these two and get this answer. In the same way, I will multiply u with the v, get this answer, multiply u with the v and get this answer. Okay, so I will show you I have done this. And the answers must be in the three significant figures. Okay, so multiply 24 with the 36, you get 864, and I will 860. 21.0 multiply 49.0, and that will be 1029. That is 1030. So 19.5 multiply 60.5, that is 1179.75. This is 1180. 18.6 multiply 71.4, and that is 1328. So that's 1330. 17.8 multiply 82.2, and that is 1463.16. That is 1460. Then they say use the grid provided in the figure 3.4 on the page 13 to plot a graph of the u multiply v, which is in meter square, on the y-axis, and d in centimeters on the x-axis. You do not need to start your axis at the origin. Draw the straight line of the best fit. Okay. So this d values, they are going to be on the x-axis. This value u multiply v is going on the y-axis. This value is starting from the 60, is going up to 90, and this reading starts from 860, and this goes up to 1460. So here we have on the next page, we have that graph. Let me show you that graph. Oh my God, we have to, okay, we have to reduce the size. So here you can see I have taken, I started from 50. So this is your 60, this is 70, this is 80, this is 90, this is 100. And the D is on the x-axis, and u multiply v I have taken on the y-axis. So I started from the 850, and 900, 950, 1000, 1050, 1100, 1150, 1200, 1250, 1300, 1350, 1400, 1450. Then I plotted those points and I draw the line of the best fit. So I hope you understand this. One of my points here. This went 2 mm up. So you can change the scale of this y-axis also. It's up to you. So here we go. Then the question is, the focal length f of the lens is numerically equal to the gradient of the line. Calculate the gradient of the line. Show all working and indicate on your graph in the figure 3.4 the values you use. Okay, the values we use. Okay, so I'm going to take on this straight line, I take 2 points. I take this point, this is 70, comma 1020. I took this point, that's 95, comma 1390. So I'm going to use these 2 points on this line of the best fit, and I'm going to find out the gradient of this line. You know, the gradient of this line is y2 minus y1 divided by x2 minus x1. In mathematics, we say this. Rise divided by run. And let me show you. Where are the solutions? So here we have. Here we go. Okay, so the gradient will be 1390 minus 1020. That is in the numerator. In the denominator, we will have 95 minus 70. So that's 370 divided by 25, and that is 14.8. So the focal length we think is 14.8. They say it will be from 14 to 17. So our answer is in this range. The lens manufacturers state that the focal length of the lens is 15 centimeter plus minus. Okay, so let me read it from here. Plus minus 10%. The lens manufacturer states that the focal length of the lens is 15 centimeter plus minus 10%. Decide with the calculation whether your value of the f agrees with this statement and tick the box that shows your answer calculation. So, I will, okay. So the difference between the actual value is 15. So our value is 14.8. So the difference is of 0.2 centimeter. So the percent difference will be 0.2, which is the difference divided by the actual value multiplied by 100. So that is 1.33%. So our value is 1.33% less than the actual value. So this is within the 10%. So my value F agrees with the manufacturer. So I will put a tick here. Our difference is only 1.33%. Okay. So hopefully you can read this. My answer. Okay, so here we have question number 4. He says this is a planning question. Plan an experiment to investigate how the thickness of a metal wire affects its resistance. The resistance of a wire can be found using the equation. Resistance of the wire is equal to the potential difference across the wire divided by the current in the wire. The following apparatus is available. We have 6 lengths of metal wire, each of different thickness: an ammeter, a voltmeter, power supply, several connecting leads, and a micrometer. Other apparatus normally available in a school laboratory can also be used. In your plan, you should draw a circuit diagram to show how you will use the apparatus. Explain briefly how to carry out the investigation. State the key variables to keep constant. Draw a table with the column headings to show how to display readings, and you are not required to enter any readings in the table. Explain how to use these readings to reach a conclusion. Okay, so very simple. So what I will do, first of all, I will make sure that all those samples of the wire, they they are of the same length. So with the help of a scale, I will check their lengths. I will make sure that each sample has the same length. Then with the help of the micrometer, I will note down their diameter. They should be of different diameters. Another very important thing is that all the wires must be of the same length. They should have different diameters, but their material is same. They are made up of the same material. This is very important. Okay, then I will take a power supply. I will connect with that power supply a switch. I will connect with it a ammeter in series. Then I will connect that that wire, and across that wire, parallel to that wire, I will connect a voltmeter. I will close the switch and I will immediately note down what is the reading on the voltmeter and what is the reading on the ammeter. And then I will change the sample. I will note down what is the length or length. We will make sure the lengths are same. Then I will take another wire which is of the, let's say, different diameter. I will note down its diameter. I will do the same procedure. I will note down what is the reading on the voltmeter, what is the reading on the ammeter. So for that purposes, obviously we will have drawn a table. In that table, we will note down what is the thickness of the wire. We will note down what is the reading on the voltmeter. We will note down what is the reading on the ammeter. And we will write a formula for the resistance, that is voltage divided by the current. So for each case, we will note down the resistance. And then what we will do, we will draw a graph, and in that graph on the x-axis I will write the diameter, on the y-axis I will write the resistance. Then I will plot these points on that graph paper, and by looking at the shape of that graph we will be able to tell that what is the relationship between the resistance and the thickness or the diameter of the wire. So this is the planning question. So let me show you. I have done this. So first of all, you know, I will draw this circuit. There we have a power supply, we have a switch, we have an ammeter. Ammeter is connected in series. Here we have a wire connected here whose resistance we want to find out. And parallel to this wire, we have connected a voltmeter. So when I will close this switch, I will note down what is the reading of the current on the ammeter, what is the reading on the voltage drop on the voltmeter. And this is the table I'm going to draw. With the help of the micrometer, I will note down the diameter, and I will note what is the voltmeter reading, what is the ammeter reading, and by using the formula R is equals to V by I will calculate every time the resistance. So I will take different wires, okay, of different diameters, same material, same length, but the diameter is different. So with the help of a scale, take different thickness wires of the same length. With the help of micrometer, note diameter of the wires of different thickness. Connect one wire with the power supply and ammeter, voltmeter, and switch as shown in the figure. The circuit diagram. Close the switch and note the reading on the ammeter and the voltmeter. Note the readings of the thickness, diameter, current, and voltage drop in the table. Divide the voltage drop by the current to calculate the value of the R. Repeat the same procedure with the wires of the same length but different diameters. Length of each wire and material should be kept same. Draw a graph by taking diameter on the x-axis and resistance on the y-axis. By looking at the shape of this graph, relation between the resistance and the thickness of the wire can be concluded. So let me reduce this size so you can see the whole thing together. So I hope you can write it in a better way, but this is one example. Let me show you the marking scheme. Here is the marking scheme of the question number 4. Better you can pause the video and you can take your time and look at this carefully. So this is how I wrote it. I hope you can write it in a much better way. Okay, so this is my answer. So we are done with this question and we are done with the paper as well. I hope this video will be helpful I hope that this video will be helpful to you. So today in this video, we have presented you the solution of the May June 2024 4-1 paper of the Physics 5054. I have tried my best to present you the solution in the written form, and I have also tried to explain you the concepts. Being a human, I might have made some error, but I have tried my best. I hope that this video will be helpful to you. If you find this video helpful and useful, please share the link of this video with your teachers, with your class fellows, with your seniors, with your juniors. You see, when you share the link of this video on your Google Classroom, in your Twitter account, on your Facebook, on your WhatsApp groups, on your TikTok, so that is very helpful for me. So I hope this video will be beneficial for you all. So thank you very much. It's a blessing for me that I can make these videos and be helpful to so many eager students around the globe. Thank you very much. Have a good day. God bless you all.